Hello and welcome back. First of all, I would like to thank you for supporting me in doing this good job. I want you to know that I always try to bring accurate and clear information to you. The sole purpose of me creating these videos is to help you understand those concepts that you always wanted to learn. At the end of this video, if you find it helpful, please do like, comment and share. If you are new to this channel, also hit the subscribe button in right bottom corner. With that being said, let's see what we have got today. So if you have already seen my previous videos, you already know that for a side-to-side tunnel to come up, it happens in two phases, phase 1 and phase 2. And they're also known as main mode plus quick mode. So the main mode is your phase 1 and quick mode is phase 2. So I've already covered main mode or phase 1, everything about phase 1 in previous videos. If you have not seen the previous videos, then I will recommend you to pause this video right here, go to the description and look for the main mode videos. So go through them, understand what main mode is, and then come back to quick mode. But if you already have a good understanding about main mode, then feel free to continue watching it. As you already know, in main mode, they exchange 6 packets or 6 messages. In quick mode, they exchange 3 messages. For a VPN tunnel to come up, there are total 9 messages exchanged between the peers. So let's see what information is shared in the quick mode in these 3 packets. Quick mode is going to be a little difficult to understand. And the reason is in main mode, there are 6 messages. So let's say we have an initiator, we have a responder. Initiator sends the first packet, responder sends the second message. Initiator sends the third message, responder sends fourth message. So after exchanging these 4 packets, both ends, initiator and responder, they generate a session key. And they use that session key to encrypt some part of the next packets. So fifth packet will now be encrypted, or you can say part of the fifth packet will be encrypted and then sent to the responder. And likewise, responder will also send the 6 messages encrypted using a session key E. So after this point, they start sending encrypted data to each other. Now they no longer send the clear text data like they did in 1, 2, 3, and 4. They send the encrypted data. So after this point, you cannot see what's actually in there because the data is encrypted. Right? So if you take a Wireshark and try to see what information has been sent in the fifth message, you won't be able to see it because that's encrypted. All you will see encrypted data and the size of the encrypted data, how much it is. Now that's the reason because they started doing that encryption from fifth message. So 7, message 8, and message 9 will also be encrypted using the same session key. So that is to protect your IKE session, so that now you can exchange your critical information and we are encrypting it. Right? So that's why if you open these packets, the quick mode messages, the packets 7, 8, and 9, this is your quick mode. If you open them in Wireshark, you won't actually see anything. That's why quick mode is going to be a little difficult to understand, because I won't be able to show you the Wireshark. Like I said, in quick mode, there are going to be 3 messages, initiator and responder. Quick mode is your phase 2. Initiator will send the first message. There are going to be 3 messages. So we say this is the first message initiator is going to send. Responder will send the second message and initiator will then send the third message. In phase 2 also, we exchange kind of similar information that we did in phase 1. And we have less packets to share that information. So like in main mode, we were sending phase 1 policies, right? And then the responder was checking which policies are matching, and then responder will select one of them and send back that let's use this. So there were lots of room to negotiate, like 1, 2, 3, 4, 5, 6. It's lots of packets exchanged between each other. So you send, I'll tell what to use. You send, I'll tell what to use. So there was a lot of room to negotiate things. But here in quick mode, there are only three messages, three packets. So there will be less negotiation. Let me go a little back and see what information did we exchange in phase one. So in phase one, we had phase one policies where the policy included information items such as hashing, authentication, Diffie-Hellman group, DH group, lifetime, and the encryption. So hashing had a few options like you can use MD5 or SHA. Authentication was pre-shared key based. Diffie-Hellman group 2.5. Right. Lifetime, so you can use any value in seconds. And encryption, so you can use AES. So these were the few items that we were negotiating in the first message of the main mode. And like I said, in phase two also we negotiate the similar information, but we do it again and we do it little, the content is little different. In phase two also we need all these items: hashing, authentication, group, lifetime, encryption, right? Because using these items only we will end up creating the keys, the encryption keys. So in quick mode, when we send the first packet, this is when we send all the information. Anything that we have to send to the responder, everything is sent in the first message or the first packet, because then there is no room to negotiate anything else, right? So anything that the initiator has, it sends everything in the first packet. And what information do we send in the first packet? So in the first packet, we send phase two policies that they're called here as transform set. If you remember, you create a transform set and call that transform set into the crypto map. Right? So that's that contains your phase two policies. There's something that is optional. It's known as PFS. So this is an optional thing. If you want, you can do it. PFS stands for perfect forwarding secrecy, or you can say it's a Diffie-Hellman for phase two. Why this is optional? You can renegotiate Diffie-Hellman for phase two, or if you don't do it, then it's going to use the same keys that it used in phase one for Diffie-Hellman. So if you remember, we did negotiate Diffie-Hellman in phase one, right? So if we do not use PFS here, then it's not going to negotiate Diffie-Hellman once again, and it's going to use the same keys that it generated in phase one. The only disadvantage is if the phase one Diffie-Hellman keys were somehow compromised, then phase two Diffie-Hellman keys will also be compromised, because phase two is also using the same keys. But if you enable PFS, then phase two will negotiate Diffie-Hellman once again and create the Diffie-Hellman keys again. And the recommendation is have it enabled. So though we say it's optional, but it's recommended to have PFS enabled. Then we also send a nonce value. Then we send a hash payload, hash value as well. So this hash payload will be hash of few values from phase one and few values from phase two. And the purpose of this hash is to authenticate the peer once again. Then there will be proposal payload. So this will include the type of encapsulation that we're going to use. Is it going to be AH or ESP? And this will also have an SPI value. Then there will be a transform payload. So this will include if it's going to be a tunnel mode or transport mode. And there will one last thing that will be there is an ID payload. This ID payload will contain your proxy IDs. Proxy IDs. So this ID payload will contain your crypto ACL. Now here is the complex part. All this information, the phase two policies, transform set, the PFS, nonce, hash payload, proposal payload, transform payload, the ID payload, all this information is sent in one packet, the first packet of quick mode. So if anything is a mismatch, you don't know which one. if any of the information sent by S does not match the information responder has, the tunnel will not come up. So let me show you the packet once again. So in the first message of quick mode, doing quick mode here, and this is going to be the first message. So in the first message, we send hash payload. This hash payload will be a pseudo random function of skid a, which was generated in phase 1. Initiator nonce, then the proposals and the transforms, the xa dash. So this means, do you know what this is? It's the public key, right? In the diff element. So dash indicates here that this has been generated once again. That means we're using PFS. Then the quick mode will have an SA payload. This SA payload will have information like about the DOI, domain of interpretation, and the situation, same as what we used in phase 1. Then we'll have proposal payload. Proposal payload will of course include the proposals, Diffie-Hellman, hashing, encryption, and SPI. And then there will be transform payload. This transform payload will have whether it's the tunnel mode or transport mode, and it will also have the timeouts. Key exchange payload. Key exchange payload will of course have the new Diffie-Hellman public key, the nonce payload, so it will have the new nonce value, and then we will have identity payload. So there will be two identity payloads. So the name will be same, but of course there will be different information. The identity payload will have information about your proxy IDs or the crypto ACL. So this, let's say this identity payload has information about local subnet, and there will be second identity payload, and this will have information about remote subnet. You can also write it as source proxy or destination proxy. This all information is going to be one packet, the first one. So let me first take a snapshot if we need to refer this again. All right, I have it now. When the responder receives first message from the initiator, so the responder also sends the similar message back with few changes. So let's see what those changes are. So let's start with the hash payload. So I'll just write hash payload. And this hash payload, if you remember in the first message, the hash payload contained the hash of SKID A, initiator nonce, proposals, transforms, and the Diffie-Hellman public key, the new Diffie-Hellman public key. But this hash payload is only going to have the payloads that are contained in this message. So that this hash payload will be considered as a kind of a proof for the responder's liveliness. So this hash payload will contain the hash of the latest nonce as well as the message ID field from the previous message. So this is just to tell the initiator that the responder is alive, to confirm the responder's identity or give it as consider it as a proof. And this will also confirm that the responder has received your first packet and it's ready to receive the encrypted data now, because there is going to be no more packets from the responder, right? Remember, the third message is going to be from initiator. So responder has to give its confirmation in this only packet that I am ready to receive the encrypted data now. So this hash also gives a confirmation that as a responder, I am ready to receive the encrypted data. This is the only packet responder has got to confirm that thing. That's why it's doing here in the hash payload. The next payload will be SA payload. So the SA payload is again going to have the same things, DOI and situation. And then we will have proposal payload. The proposal payload will have the accepted proposals and the SPI values. And we will have the transform payload. Transform payload will have the accepted transforms, like what has been accepted, tunnel mode or transport mode, and the timeouts. The next payload will be key exchange payload. This key exchange payload will have the Diffie-Hellman public key of the responder, xb dash. Nonce payload. So the nonce payload will have the nonce value. Have identity payload. There are again going to be two identity payloads. So one of them will have the local identities, the source identities, and another will have the remote subnet IDs. So you can say ID of destination. This is going to be similar to what the initiator had sent. So let me take a screenshot of this as well, and so that I can show you the comparison. And now comes the time to send the third message from the initiator. The initiator sends the third message to the responder. Before sending third message, both initiator and responder, they have exchanged some information in first and second packet, and I would say not some information, all the information they have exchanged in first and second packet, right? So if there was anything that was not matching, or if there was any mismatch between their parameters in first and that was sent by the initiator in the first message, and let's say something did not match on the responder, so responder will not reply with the all the parameters in the second message, instead send an informational message telling that some few things do not match, so I'm not going to continue this negotiation with you, right? But if everything matches, then there is going to be the third packet. And before sending this third packet, and after responder is done sending the second message back to the initiator, they both, initiator and responder, they do some calculation. In both first and second message, they've exchanged their Diffie-Hellman public key, the new Diffie-Hellman public key, xa dash and xb dash, right? These values have been negotiated in the key exchange payload. Now using this key exchange payload, they generate a new Diffie-Hellman shared secret, similar to what we did in the phase 1. So if you want more details about how this was generated, you can go back to the previous videos and check this out. So they generate a new Diffie-Hellman secret. This is done on the both sides. And then using these Diffie-Hellman secret, the session ID, the ASCII IDs, and some other parameters, they generate encryption and decryption keys, the IPsec encryption and decryption keys. The initiator generates the session keys for inbound, a pseudo-random function, ASCII-ID protocol ICAM, the new Diffie-Hellman shared secret, the responder SPI, the new initiator nonce, and new responder nonce. So using these values, the IPsec session key for inbound traffic is generated. And the initiator also generates IPsec session key for outbound traffic. So session key for outbound traffic. Formula is going to be pretty much similar. Pseudo random function session key ID D, SKID D protocol, and the new Diffie-Hellman shared secret PI of initiator, the initiator nonce, and responder nonce. And in the similar manner, the responder also generates the session keys, so for both inbound and outbound. So let's say on the responder side, the IPsec session key inbound is going to be exactly same that was generated on the initiator side for outbound. So the formula is, you can say it's going to be exactly same. So this goes here and this goes here. So whatever key is used on initiator side for inbound traffic, that will be used for outbound on the responder end. And the key that is used on the initiator side for outbound traffic will be used as inbound on the responder side. This all is done before sending third message. They both generate these keys independent of each other using the same values that they've already negotiated, right? And that's why these keys are going to end being same on both the sides. So once these keys have been generated, it's pretty much ready. Third message is sent by the initiator. Initiator sends the third message, and in this third packet, it sends proof that I'm live. So it just sends a proof that I'm live. And how it does that? Initiator sent the first packet. The responder replied with the second message. In the second message, responder also replied, because responder knew that this is going to be the only packet that I'm going to send. So in the second message itself, with the help of hash payload, the responder made sure to let the initiator know that I'm live and ready to receive the encrypted traffic. The responder has already given the proof of live. After exchanging first and second messages, they processed the data and came up with the IPsec encryption and decryption keys, right? Once the keys have been generated, now the initiator will send the third message. In the third message, it sends a proof of life by sending the hash payload only. So the third packet will only have a hash payload And this hash payload, it is going to have the hash value of the new initiator nonce and new responder nonce. And with the help of that, it confirms that I'm live and I have received your second packet and successfully processed it. This will be a hash of the new initiator nonce value and new responder nonce value. Once that packet is sent, there is nothing else required for either from the initiator or responder. So once it has been sent from the initiator, the tunnel comes up. The initiator does not wait for any confirmation. The tunnel comes up. So let me show you some debugs. I'm just going to enable the debugs from my tunnel. So I have this VPN tunnel with 72.163.5.144. You can enable these debugs in live environment as well, but you have to do it exactly the way I'm doing it right now. You have to enable your debugs conditionally just for your particular VPN tunnel that you're interested in, and do not enable the debugs for everything, right? So I'm just going to take this IP and say debug crypto condition peer and the peer IP. So that's how you tell the ASA to enable the debugs just for this particular VPN peer, right? And sometimes what happens that when you have multiple VPN tunnels and multiple people managing the device, so they might also enable the conditional debug for some other VPNs and forget to remove them, right? Or forget to disable their debugs when they leave this session. So that keeps the condition there. If someone else has enabled some conditional debugs, the way to do that is show debug crypto condition. And you can see there is only one IP in the filter, and that's that 5.144. If you see more than one IPs, you'll have to turn off the debugs and get rid of that and then enable it again. Right now, only my IP, my required IP is in the condition. I'm going to enable the main debugs now. So I say debug crypto IKV1 128 I do. And then I'm say debug crypto IPsec 128. Alright, so we have the debugs in place. Let's initiate some traffic. So I'm going to initiate some traffic from my other computer in the LAN. Let's see what happens. So there you have. I've stopped the ping. So let's look at this debugs. So I'm not going to show you the phase 1 debugs once again because we have already done that in previous videos. So if you want to see how to troubleshoot or how to read debugs for phase 1, you can watch the previous videos. Look in the description, you will see the link there. Now once it says phase 1 has been completed, let's see what happens then. So after phase 1 completed, it starts the phase 1 rekey timer and starts to negotiate phase 2. Here it says Initiator sending first QM packet. So it's sending the first message now. That means whatever this thing is done before sending the first message. So let's see what it has done. So I got SPI from key engine. So it has generated one initiator SPI. Then constructing quick mode, constructing hash payload, IPsec SA payload, nonce payload, key exchange payload, the PFS key exchange payload. PFS stands for perfect forwarding secrecy, which is a Diffie-Hellman for Diffie-Hellman for phase 2. The proxy IDs, constructing proxy IDs, right? Transmitting proxy IDs. So these are the proxy IDs we have. The crypto ACL. The local subnet is 1042.166.0 and the remote subnet is 192.168.7.0 and both are /24. So you can see that information right here in the debugs. And then it says Initiator sending initial contact, constructing QM quick mode hash payload. So that's the hash payload. Right now this was a constructing blank hash payload and now this is the actual hash payload. Right, Initiator is ready to send the first quick mode packet with this message ID. Right, so Ike decode sending message ID this. So just notice the message ID, it's same as this. That means it's still the first packet. So it has a header, hash, SA, nonce payload, key exchange payload, ID payload, or ID payload again, identity payload. So all this the payloads that we just discussed. Ike decode received message with this message ID. So it has received a message from the responder with the header, hash, and it says delete, and there is nothing else. But we were expecting the similar payloads, right? So instead we got delete message from the remote end. And then we start to process it. So processing hash payload, processing delete. In the delete, it has said terminate. So the connection terminated for the peer. And then we send the delete to the peer that we have deleted. He also delete. So we are sending Ike decode sending message. We send header, hash, and delete. And then the session is being turned down. Reason user requested. So that's not the actual reason that user has requested for it. And then it says removing peer from correlator table failed, no match. I'm just showing the debugs again here. This was phase 1 completed, and then it starts the phase 2, creating all these payloads, sending the first quick mode packet, and then this is the actually sending. This is when it's actually sending the packet. And this is the received one, where we received the delete payload. All right, so what do we know from these debugs? What's happening? Removing peer from correlator table failed, no match. So you get this error message when usually there is a mismatch in phase 2. It can be a mismatch of transform set, can be a mismatch of the crypto but as we know it's not, because I've made sure that all the crypto are fine. The reason we are not seeing lot more information about why it's steering down the tunnel, because we are the one who is initiating the VPN. So we are sending something that the remote end does not like. And that's why the remote end is sending us a delete message. You see, we sent the first quick mode message, and then we receive a delete from the remote end, right? That means in our message there was something that remote end does not like, that's not configured there, not supported, and that's why it has requested for a delete. That delete the tunnel, I don't like this, right? So if you are not seeing really a valuable information in your debugs, then it will be a good idea to have the same debugs on the remote end. So let me get access to the remote end, and we'll take the debugs there. Alright, this is the second ASA. Let's enable the debugs here again. So show run crypto map. I want to make sure I know my peer IP so that I can have the conditional debugs enabled. So I'll say debug crypto condition peer and the peer IP. Once I have the conditional debug enabled, I would like to verify what condition do I have. So I'll say show debug crypto condition, and that will confirm my peer IP. Once you have done that, let's enable the actual debugs. So debug crypto ISIC M128 and debug crypto IPsec 128. Let me go back to my PC and run the traffic once again, and you will start to see the debugs. The ping is running. I've stopped it now. Debugs are going to stop as well. Undebug all. That's how you stop them. Once you have done undebug all, let me show you this. Check the debug condition again, and there is none. So once you do undebug all, it automatically removes your conditional debug. But at times you forget to do undebug all, and your session times out. Your SSH session to the firewall times out, and that is when it leaves that conditional, the conditional debug that you have entered in the filter. Let's take a look at the debugs, and I'm seeing little more different debugs here. As you can clearly see, this is where phase 1 completed and phase 2 processing started. So because this guy is responder, so it has not created the first packet, it has received the first packet, right? Responder starting QM quick mode, and received message, so it has received the header hash SA nonce key exchange ID processing the payloads, processing hash payload, SA payload, nonce payload, key exchange payload, processing ICAM key exchange for PFS in phase 2, ID payload. So it, after processing the ID payload, it is also showing what ID or the what proxy IDs have been received. So IPv4 address subnet ID received 1042.166/24, right? This was the local ID. So and received remote IP subnet data in ID. So this is the remote IP 1042.166, and we'll also show you the local ID. So these are the local ID. So received local IP proxy subnet 192.168.7.0. Processing notify payload, and then it says tunnel rejected. Conflicting protocols specified by tunnel group and group policy. That's why it's sending a delete, because it doesn't like the protocol. So let's see what it doesn't like in the protocol. So it says conflicting protocols specified by tunnel group and group policy. So we have to look at the tunnel group and group policy configuration. So show run tunnel group and the tunnel group name. The tunnel group name for a site-to-site VPN is usually the peer IP. So my tunnel group does not have any protocol. Let's check the group policy. I don't have any group policy here. So if you do not specify any group policy in your tunnel group, it automatically takes the default group policy. And how do you see the default group policy? You say show run all group policy. That's how you see the default group policy. So you see, come on, group policy, default group policy. So it talks something about the protocol. So I have VPN tunnel protocol and it is set to IKE version 2, but I'm doing a tunnel that that has been configured as IKE version 1. So this is the mismatch. The group policy says let's do IKE version 2, but the tunnel configuration says let's do IKE version 1. So we have to fix this thing. And how do we fix it? Let's enable the IKE version 1 as well in the same group policy. So you can do config T, go to group policy attributes. So we're gonna enable both of them, IKE version 1 and IKE version 2. It's not necessary. If you are not using IKE version 2, you can of course get rid of that. Let's verify the tunnel protocol here as well. Show run all group policy. So the tunnel protocol is IKE version 2. So here I'll show you that we can get rid of this and only have IKE version 1. So I'll say no, and there you go. Let's verify show run all group policy. You only have IKE version 1 now. You might be wondering, why am I saying show run all group policy and not just show run group policy? Because if you do show run group policy, it will only show you the custom changes that you have done or the custom group policies that you have created. So this is the custom thing that I've done in the default group policy. Then why then I'm seeing it here, right? Otherwise it doesn't show the default group policy when you do show run group policy. It only shows you the policies that have been manually created, and the default one is it's by default. You don't create it, it's there already. So it looks like we have everything in place now. Let's have the debugs enabled once again. So sure, on crypto map, I need my peer IP. Debug crypto condition peer and the peer IP, duplicate address in the filter table. Okay, so let's check the debugs. What debugs do I have? Show debug? Debugs are already enabled here with this as a filter. Alright, let's have some traffic. So initiating ping, should see the debugs now. Stop the ping. Alright, good to see. Phase 2 completed. Phase 2 completed, my dear friend. And I have just sent 5 pings. So I'll show you where you can see that. The good news is phase 2 completed. Let's quickly take a look at these debugs. What information do you see more? I'll just say undebug all so that nothing else comes in when we are looking at them. So similar thing here. Once the phase 1 has completed, it starts the phase 1 rekey timer and starts to create the first quick mode packet. And before sending the message, it creates few payloads, sending the first quick mode message with header, hash, SA, nonce, key exchange, ID, notify, and then it received, and the received message, it says header, hash, SA, nonce, key exchange, IDs. It's similar thing. It is processing the received packet and extracting the information. So if it finds loading all IPsec essays, generating quick mode key. So that's what I told you, that after they've sent first and second packet, then they start generating the keys. Right, so it looks at the crypto map and constructing final quick mode. So you see it has generated these SPI values here. The inbound SPI S351 and outbound SPI is something like ends with DFT. Let's just copy them. I wanna show something. So let's copy these SPI values somewhere in a notepad. Here they are. Right, I've copied them. So these SPI values has been created, and then it sends the final quick mode message sending third quick mode packet. In the third quick mode packet, it sends header, hash, and nonce. None. Sorry, not nonce. It only sends a hash value. Then the security associations have been created, which binds itself with these SPI values that we have just created. Right, so there were two SPI values. This one. Let's take a look at this notepad that we just copied. So inbound SPI, you see this ends with 351. Here, this is outbound section. Anyways, let's look at the outbound SPI then. So here this says outbound SPI is 58229 DFT. So this is outbound SPI 58229 DFT. The tunnel type is L2L, protocol is ESP, lifetime to 40 seconds. So it creates a kind of VPN context for it, which will store the encryption keys, encryption or decryption keys that they are going to use. So these are not the keys. The SPI values you see, they're not the keys, but they're reference to the keys that are going to use. Right? So we cannot have the keys displayed right there. So they are stored in the database, and this is the reference number. So when it points to this SPI, that SPI points to that particular key stored in the database. That's how they are. That's how it works. And this was for outbound, the direction outbound, and we'll also have for inbound. So this is for inbound where the SPI is 351. So it creates a VPN context, creating inbound VPN contexts for SPI 351, where it stores the SA, SPI, the peer, so all these values. Alright, and finally it says phase 2 completed. So after once it is done sending the third message, it will just simply say phase 2 completed. Now, how do you check your phase 2 is up and what's happening in the phase 2? So you say show crypto IPsec SA, before showing phase 2. Let's check the phase 1. So show crypto IPsec SA, and that tells active means main mode is up. So your phase 1 is up. Show crypto IPsec SA peer IP, that shows you phase 2. So this is your crypto ACL, local identities, your local network, remote identities, the remote network, and the current peer IP, what crypto access list is matched, how many packets have been encrypted, how many packets have been decrypted. So it shows you that information, right? And interestingly, it also shows you the information about the SPIs that we're talking about. So inbound ESP essays and outbound ESP essays, right? Because it has to refer to that database, right, where it has the key to encrypt and key to decrypt. So that's why it creates this essays here with the SPIs as a reference. So you see the SPIs are still same, D351 and DFD. I'll just open that notepad once again. So D351 is the inbound. So you see inbound here. Let me take the pen. So the inbound SPI here 351 matches the inbound SPI here 351, right? And same goes for the outbound SPI. So outbound SPI ending with DFD matches the outbound SPI here DFD. So they are the same SPI values, right? And like I said, this SPI value is just a reference to the actual key database that is being used to encrypt and decrypt. So once it sees this SPI, it matches to the particular database. Right. This output is a little lengthy. So what I do to compress the output and see the only thing that's required, I do pipe include ident and pkts. So usually the problems are like packets are encrypting, not decrypting. How many you want to see how many packets are going, how many packets are coming. So you can use this. If you need to see the SPI values, then of course run the direct command. Do not filter it. So you will be able to see the SPI values as well. It also mentions the inbound and outbound SPI here. That's all for now. I hope this has been informative to you, and I would like to thank you for watching it. It is your support, your likes, comments that keep me motivated for bringing up more stuff like this. Please let me know if this has helped you. If you are new to this channel, also hit the subscribe button and right button